In our last class, we have seen that the bulk crystal growth takes place using one technique which is known as Choralovsky technique. And we have discussed in detail that in Choralovsky technique what happens, the silicon is kept in a crucible. The crucible is made of generally quartz, that means silica, and high temperature is required because the melting point of silicon is very high. So, the effect of the growth is that in some cases you will find that there will be contamination. If you see this view graph, you will see that this is the crucible, this is the silica crucible, okay, and it is in touch with the crucible wall. So, what you find that particularly the oxygen or different kinds of contaminations will be there in the melt of silicon, because silicon is in the liquid state, it is almost the melting state. And there is another technique in which we can avoid this kind of contamination from the crucible, and that is known as the float zone silicon crystal growth. Okay, that is known as the float zone silicon crystal growth. This float zone silicon crystal growth is a technique in which we do not use crucible. So, you see that it is a crucible free technique, we do not use crucible. So, contamination is scarcely introduced during crystal growth. Basically, there is no contamination during crystal growth, and oxygen concentration is also very low. It is approximately 10 to the power 15 atoms per centimeter cube, and so the resistivity is very high. It is 400 ohm meter, remember, not centimeter, ohm meter, it is very high. And due to this high resistivity, float zone silicon is used for rectifiers, thyristors, power transistors, that means which are known as the discrete power devices. Okay. So, what we find that due to crucible free, there is no crucible in this technique. I shall show you the diagram for this kind of crystal growth, and if you compare this crystal growth with the previous one, that means Choralovsky technique, you will find that there is a crucible associated with this type of a technique. There are other kind of differences apart from this use of crucible, is that the seed crystal is placed at the molten state, at the surface of the molten silicon, and then pulled. And in this case, we shall show you that the seed crystal is placed on the bottom, not on the top, right. Then because of there is no contamination, you will find that the resistivity is very high. You know that if there is a iota of impurity, the resistivity decreases, because you know that if a semiconducting sample is not doped at all, that means it is known as the intrinsic. So, if the semiconductor sample is intrinsic in nature, the resistivity is very high. That means intentionally or unintentionally you have not doped the sample with any kind of impurity. Okay. So, that is the difference between the intrinsic and extrinsic nature of the material. So, in Choralovsky technique, you will find that from the crucible itself there will be impurity. Apart from silicon, oxygen, there may be carbon or other kind of impurity. Carbon is another kind of impurity which is readily available during crystal growth. What is the source of carbon? The source of carbon is, you know that there is furnace, then there is heater, then graphite susceptor. So, from those kind of material always there will be carbon emission in the form of carbon monoxide or carbon dioxide, and they will be absorbed in the silicon melt. So, that means during Choralovsky technique growth, you will find that there is many ways through which the impurity can be associated in the melt, giving rise to some increase in conductivity, that means decrease in resistivity. But there are some application, particularly you will find that the application in discrete power devices, that means the devices are known as rectifiers, thyristors, power transistors, etc. Very high resistive sample is required, material is required. So, that means this material must be free from any kind of impurity, and that is why no contamination is allowed in this case, and you will find that due to the contamination the resistivity decreases. So, if there is no contamination, the resistivity increases, and you find the value is 400 ohm meter, is quite high value. And in this float zone technique, generally a high purity polycrystalline rod with a seed crystal at the bottom is held in a vertical position and rotated. Here also you find that the starting material is polycrystalline silicon, and in our last class we have discussed about the synthesis of high purity polycrystalline. Can you remember? We have synthesis the very high crystalline, high purity polycrystalline of the order of 10 N or 11 N purity. So, in almost all the cases, be it Chouralski technique or float zone technique, the starting material is high purity polycrystalline silicon. And here also a high purity polycrystalline rod with a seed crystal. Now, what is the necessity of seed crystal? Why we use a seed crystal for the growth of any crystal? Why it is required at all? Yes, basically we know we want a particular orientation of the crystal 100, 111, 101, any particular orientation. So, there is a melt and it crystallizes using the technique of solidification, and during solidification if you introduce one seed crystal, so the crystallization takes place in a better way with a particular orientation. So, that is the reason that you will find in almost all crystal growth technique, be it bulk or epitaxy, there is a seed crystal. In epitaxy, the seed crystal is basically the substrate on which the growth takes place. Basically, the substrate on which the growth takes place. So, in the direction of the surface of the substrate, the epitaxial growth takes place. So, in this case you find that we start from a polycrystalline very pure silicon rod and the seed crystal at the bottom held in a vertical position. You see that this is a silicon, high purity silicon rod, this is, and there is a seed crystal at the bottom which is placed in a vertical direction, right. So, now if you find the difference between this thing and the Chouralski, what you find? Here you see that there is no crucible, and in Chouralski you will find that there is a crucible. In Chouralski the pull is taken from the upward direction, here it is in the bottom direction, you will find that the crystal growth takes place. Now, the rod is enclosed in a quartz tube with inert atmosphere inside, it is as usual. There also you find that in Chouralski technique there is a quartz atmosphere, it is covered with a quartz tube and the argon is passed through the quartz tube. Why the argon was necessary for the crystal growth? Yes, to replace basically oxygen etc., and to control the oxygen which comes from the crucible. Another thing is that the graphite susceptor is used and oxygen is very detrimental at high temperature, it will be oxidized and it will be damaged. So, that is why inert atmosphere is maintained inside the quartz tube within which the total growth system is housed. Here also you see that the rod is enclosed in a quartz tube with inert atmosphere inside. That means, this is your rod and it is fully covered with a quartz tube, quartz tube and inside there is a inert atmosphere. A small portion of the crystal, this small portion is known as the zone, Z-O-N-E. So, the name of this technique is float zone technique. Zone comes from this concept that a small portion of the crystal is kept molten by an RF heater, radio frequency heater. This heater is moved from the seed upward, so that the floating zone moves along the length of the rod. So, the float zone comes from this concept that the zone moves. That means, you see that the heater is moved from the seed upward. You see, this is your RF coil. So, that means the RF coil imparts heat to this rod. So, it is in a molten state and this RF coil is moved upward direction. So, that means this zone is not fixed here. The zone was earlier here near the seed, then the zone moves upward, and since there is a seed and it is pulled in this direction downwards. So, due to the temperature gradient of the molten state and between the solid liquid interface there is a temperature gradient, it solidifies, that means freezing effect is there and the single crystal grows in this manner. So, at the end what will happen? The whole rod will become single crystal because of this movement of the heating source, that means the molten zone is moved. So, that is why it is known as the floating zone, it is floating basically and it moves along the length of the rod, and you see that this molten silicon is retained by surface tension between the solid liquid interface, that is the melting and growing solid silicon phases. There are two phases, one is the growing, that means where it solidifies, and another is the molten, that means where the RF coil is there. So, because of the surface tension between these two interface, it is held there, it does not detach from its position. As the floating zone moves upward, see the spelling mistake, floating zone moves upward, a single crystal silicon solidifies at the zone's retreating end and grows an extension of the seed crystal. Retreating end means this end, this is the retreating end. So, as it moves, crystal increases, the single crystal increases as it moves upward. It can be used to purify the crystal very easily, no crucible and no contamination. That is the most important advantage of the float zone technique, that because of no crucible, no contamination takes place, and so it can be purified very easily. Why this term purification we use? We use this purification term because you see that when the crystallization takes place, generally all bulk crystal is made using the melt growth process. That means, first the material is melted and then it is pulled using a seed crystal. So, when the crystallization takes place, always you will find that the impurity distribution in the crystal, that means in the bulk, is less compared to the molten state. That means, if X is the impurity concentration in the melt, the solid will not have X, it will be less than X concentration. Why? Because why it happens? Because of the solidification, the temperature is maintained in such a way that the solidification takes place of the silicon material itself, right. If there is an impurity, then what will happen? Solidification temperature will be different, 1 degree, 2 degree, 4 degree may be different, but here the temperature is maintained in such a manner that even plus minus 1 degree centigrade is not allowed. So, most of the impurity is rejected in the melt, and as the crystal grows gradually, melt becomes impurity rich. Earlier it was X, right, then the quantity decreases, melt quantity decreases, but the rejection takes place manifold. So, the melt will be increasingly impurity rich. Let us take one concrete example. Suppose we want to dope silicon with phosphorus. So, what will happen? We generally mix phosphorus in the silicon melt. There is calculation, I shall show you how the calculation is done. If you take 10 kg, 40 kg, 50 kg, 100 kg of silicon, then what should be the quantity of arsenic or phosphorus or boron if you want to dope it by 10 to the power 16 or 10 to the power 17 per cc impurity. So, you put some phosphorus in the silicon melt, right. Suppose you have given 10 to the power 18 phosphorus in the melt, but after the growth you will find that it will be 10 to the power 16. In the solid it will be 10 to the power 16, not 10 to the power 18. But as the silicon, because the melt is silicon plus phosphorus. So, as the more and more silicon is consumed, so what will be there? The phosphorus quantity percentage will increase inside the melt. So, the melt will be rich in phosphorus. So, eventually what will happen? The whole crystal will grow. At the end it will be full of impurity. So, generally the tail is sliced out from the main crystal, because the impurity is very high in the tail region, and also the neck, that means the seed region, it is also chopped off, because if you see a crystal from the seed, you can imagine that there will be a shoulder due to the seed and there will be a tail at the end. So, the tail and the shoulder are both chopped off from the crystal, so as to avoid the impurity inside the material. Now, what should be the dopant distribution? You see that a known amount of dopant is added to the melt. Known amount means it may be gram or milligram of phosphorus or arsenic or antimony or boron is added to the melt to obtain the desired doping concentration in the grown crystal. When we say crystal, that means it is the solid. When you say the melt, it is basically the liquid, that means it is in a molten state. Doping concentration in the crystal, that means in the solid, is different from the doping concentration of the melt, that means liquid. The ratio is known as segregation coefficient or distribution coefficient. What is this ratio? This ratio is the doping concentration in the solid. You see that it is C suffix S, S stands for solid, and it is C suffix L, L stands for liquid. People have taken the experimental data to obtain this CS and CL, and they found that in almost all the cases it is less than 1. Okay. So, if the ratio CS by CL is less than 1, what it implies? It implies that the impurity is rejected to the melt. Ideal is 1, ideal is 1, that means almost all the impurity is taken up by the crystal as per your calculation. But if it is less than 1, you will find that it means that there is a rejection of the impurity in the melt itself. So, the K0 or Kd, in some books you will find that it is written as Kd or simply K, it is the segregation coefficient or the distribution coefficient of the impurity in the crystal. and you can see that the values of the distribution coefficient for different kinds of dopants in silicon. You see that the dopant is boron, aluminum, gallium, indium, all those 4 dopant give rise to p type doping. Here the type is given, and the segregation coefficient you see 0.8, for boron it is 0.8, for aluminum it is 2 into 10 to the power minus 3, very very less. Gallium 8 into 10 to the power minus 3, indium 4 into 10 to the power minus 4. So, likewise you see that except oxygen, oxygen it is very high 1.25, for almost all other cases you will find that it is less than 1. Okay. So, that means if K 0 is less than 1, so Cs must be less than Cl, Cs must be less than Cl, because K 0 is nothing but the ratio of Cs to Cl. And there are other 2 dopant, you see that copper and gold. You can dope silicon with copper and gold, but you will find that they will give rise to deep level. What is deep level? Can you say what is deep level? You see that when impurity doping takes place. So, let us draw the silicon, it is the conduction bandage, it is the valence bandage, and the value is how much? 1.12 electron volt. This is silicon. This is Fermi level, intrinsic Fermi level. It is at the mid CAF, that means 0.6656 electron volt. Now, when we talk about doping, basically those are shallow in nature, shallow, SHALLOW, those are shallow in nature. That means for donors, they will occupy the position just below the conduction bandage, and for acceptor type of thing, they will occupy the position just above the valence bandage. Okay. So, that is why they are shallow in nature. That means these levels, these are the shallow levels very near to the conduction bandage or valence bandage. That is why they are shallow. And another thing is the deep level. As the name implies, they will occupy the position deep inside the band gap. That means these positions. So, they will not contribute to the conduction mechanism. They will not contribute to the conduction mechanism. Why they will not contribute to the conduction mechanism? Why they will not contribute to the conduction mechanism? It is because the ionization energy will be very very high, and who will supply that ionization energy? The semiconductor is popular because at room temperature is conducting in nature, because from the normal thermal value, thermal energy kT, almost all the donors or the acceptors are ionized, okay, because the value is of the order of some millivolt, milli electron volt. But if there is a deep level, the ionization energy is so high that at normal room temperature or operation temperature, the impurity will not be ionized. So, if they are not ionized, they will not give you the electron or hole for the conduction mechanism. Say, see, this is the shallow level, and this shallow level, the difference is say milli electron volt. What is the room temperature thermal energy? It is 26 milli electron volt. It is 25.9 milli electron volt. So, with that temperature, almost all of the donors will be ionized. So, if the donors are ionized, for each donor atom one electron it will donate to the conduction band. So, at the conduction band you will find many numbers of electrons coming out from the donor atoms, and the donor atoms will be ionized. The donor atoms will be ionized, immobile ions will be there. Similarly, for acceptors, the holes will be given, that means, it will act as acceptor. There will be many states which can accept the electrons. So, that is the conduction mechanism in semiconductor, but the deep levels will not contribute to either electrons or holes, because of the position they are occupying is very deep so far as the conduction bandage or valence bandage is concerned, and consequently such huge amount of energy they will not be provided. Say if it is near the mid gap, so what is the value? The value is 0.56 electron volt, almost 0.5 electron volt. So, 0.5 electron volt is very high value for semiconductor. 0.5 electron volt is very high value for semiconductor, and if you consider 0.56 electron volt, what should be the thermal energy, what should be the temperature which will give rise to 0.56 electron volt? That means, kBT equals to 0.56. So, T equals to 0.56 divided by 1.38 into 10 to the power minus 23. So, it is very high value, very high value. At that high value, the silicon will not remain as silicon, and also huge power will be consumed. So, the spirit of semiconductor technology will be lost, because semiconductor needs very small power and miniaturization. So, that will be lost. Okay. So, you see that for silicon, the copper and gold, they will give rise to deep level, they will not form either N type or P type conductivity in silicon. Now, this K 0 equals to C s by C L, that is known as the segregation coefficient. Now, let us make some small mathematics, very small type of mathematics. You see that suppose there is a crystal, the initial concentration, dopant concentration is say C 0 in the melt, it is in the melt, and M 0 is the initial weight. M 0 is the initial weight. Then as the crystal growth takes place as it approaches, then what will happen? Some of the crystal will be solidified, say M 0 is the initial weight. So, you see that there will be M 0 and say there is, as M 0 progresses. So, S is the dopant remaining in the melt. So, minus d s will be equals to C s into d m. What is d m? d m is the amount of crystal which is being produced, very small amount of crystal, say d m. M is the total weight. So, d m is the infinitesimally small weight, and you know that S is the dopant remaining in the melt. So, why it is minus? Because it is rejected, it is rejected. So, we can write minus ds equals to Cs into dm. What is Cs? Cs is the concentration of the dopant in the solid state, that means in the crystal, it is in the solid after solidification, right. Another expression we shall write that, so remaining weight equals to m 0 minus m. M 0 minus m is the remaining weight of the crystal, and doping concentration in the liquid equal to C L. So, we write that C L equals to S by M 0 minus M. Okay, let me explain again. Let the initial dopant concentration in the melt is C 0, dopant, and initial weight is M 0. M at certain instant of time, say after time t, m amount of crystal is grown, m amount of crystal is grown. So, and S is the dopant remaining in the melt. So, we can write that minus ds equals to Cs into dm. Why it is minus? Because it is decreasing, it is rejected to the melt. So, it is, that is why it is minus ds equals to Cs into dm, m at instant of time the weight of the crystal, that means in the solidifying state. Okay. Now, what is the remaining weight? The remaining weight is m 0 minus m. Then the doping concentration in the liquid, if I consider that Cl, so Cl will be S by m 0 minus m. M 0 minus m is the remaining weight of the crystal, because initial weight was m 0 and at any instant of time t, m is the weight of the crystal. So, m 0 minus m is the remaining, and S is the dopant remaining in the melt. So, dopant remaining in the melt minus the weight of the crystal will give you the doping concentration in the liquid, which is Cl. Now, if you put these two, if you join these two equation, you will find that ds by S, it is equals to minus k 0 dm by m 0 minus m. You see that first equation was this thing minus ds equals to Cs into dm, and second equation was Cl equals to S by m 0 minus m. Using these two equation, I can write ds by S equals to minus k 0 dm by m 0 minus m. Why? Because you know that k 0 is equals to how much? Cs by Cl. So, if you put Cs by Cl equals to k 0, you can arrive at this expression. Now, I want to integrate this thing. Then what is the limit? Limit is that here for S, you see that it must be S the final and C 0 m 0 is the initial, because when the weight was m 0, the concentration was C 0. So, C 0 m 0 was the initial limit and S is the final limit, because we have already assumed that S is the dopant remaining in the melt.
In this expression, the weight of the crystal is decreasing.
Weight of the crystal, no, weight of the melt will be decreasing.
Initial weight is m 0.
M 0, yes. and if m crystal is grown, so that means m amount is consumed. If m weight of the crystal is grown, that means m melt is consumed. So, the remaining will be m 0 minus m. Your melt was m 0, that means total crystal will be m 0, right, and m amount of crystal has grown, m by weight obviously. So, that means from the melt m 0 amount is consumed. So, remaining is m 0 minus m. And in this case you will find that minus k 0 dm by m 0 minus m, it must be from 0 to m, because the crystal is grown up to the weight m at any instant of time. Then if you solve this equation, what you will get? If you solve this equation, what you will get, or what will be there? ln s C 0 m 0 s, it is equals to minus k 0 into ln m 0 minus m 0 to m, or ln s by C 0 m 0 whether it is okay? Which one? This one. Okay. Hmm?
How the limits of ds upon s comes?
Which one?
C naught m naught to s.
C naught m naught is the initial doping concentration, and S you see that the dopant remaining in the melt is S, we have assumed, and initial doping concentration was C 0. So, C 0 by weight, that means 1 gram of the crystal, C 0 is the doping concentration. So, for m 0 it is C 0 into m 0. Okay. Then you see that from this expression we can write ln S by C 0 m 0, it, which one? Which one? It will be m 0, yes, it will be m 0 to the power k 0, right. Now, you put the value of S. What was the value of S? This was the value of S. This was the value of S, Cl into m 0 minus m. So, you put the value of this thing, or okay. Then you put this equation, that means C s by C L equals to k 0, this thing. In place of C L, you can write C s by K 0. Here you see in place of Cl you write Cs by K 0. In place of Cl it is Cs by K 0 into C 0 1 minus m by m 0, it is ln 1 minus m by m 0 to the power K 0, okay, right. Next is you can write 1 equals to ln 1 minus m by m 0 to the power K 0 by C s by K 0 C 0 1 minus m by m 0. It is okay. Then what will happen? It is ln A by ln B, ln A minus B. So, you put here what will happen? 1 equals to, you can calculate. Why?
ln A by B equals ln A minus ln B. It is ln A minus upon ln B.
Okay. Let me see the calculation again.
Just put out the ln.
Okay, okay. You up to this it is okay.
Next page.
Up to this it is okay.
Yeah, so put K0 onto the
No, no, no. You do one thing,
power.
or yes, ln S by C 0 m 0, it is equals to ln 1 minus m by m naught to the power K 0. Then you remove the log. Then you remove the log. Okay. Then you remove the log. Then what will happen? Or S by C 0 m 0, it is equals to 1 minus m by m 0 to the power K 0. Now replace S, fine. Now replace S. S equals to how much? CL CL upon C naught
Into 1 minus m over
1 minus, it is equals to 1 minus m by m 0 K 0, or CL by C 0, it is 1 minus m by m 0 to the power K minus 1, right, or C s equals to K 0 C 0 1 minus m by m 0 K to the power minus 1 K minus 1. That means, here you see that I have replaced CL with CL equals to CS by K 0. Okay, okay, okay. Right. So, this is the expression for the dopant distribution in a float zone technique, and this distribution is applicable for any kind of crystal growth where the doping is takes place, right. That means, C s equals to K 0 C 0 into 1 minus m by m 0 K 0 minus 1, where C s is the dopant concentration in the solid, K 0 is the segregation or distribution coefficient, C 0 is the initial doping concentration, m 0 is the initial weight of the crystal, and m is the weight of the crystal after time t say, right. So, this is the expression C s equals to K 0 into C 0 1 minus m by m 0 into to the power K 0 minus 1. So, this is the dopant distribution in a crystal in terms of the segregation coefficient. Now, let us take one example. This example we can take, say, this thing. A silicon crystal is to be grown by Czoralski method, and it is desired that the ingot contain 10 to the power 16 phosphorus atoms per centimeter cube. What concentration of phosphorus atoms should the melt contain to give this impurity concentration in the crystal during the initial growth? For phosphorus in silicon, K0 is given as 0.35. If the initial load of silicon in the crucible is 5 kg, how many grams of phosphorus should be added? The atomic weight of phosphorus is given, it is 31. So, there are two parts. One part is that what concentration of phosphorus atoms should the melt contain to give this impurity concentration. What is the impurity concentration? 10 to the power 16 phosphorus atoms per centimeter cube. Another thing is that how many grams of phosphorus should be added. So, here for this problem, first you have to calculate CS. So, you calculate CS. You calculate CS. CS equals to how much it is? CS K0 equals to CS by CL, or CL equals to CS by K0. CS is given how much? 10 to the power 16 by K0 is 0.35. So, how much? It comes out to be 2.86 into 10 to the power 16 centimeter cube inverse. Yes, CS is given. Yes, question is what concentration of phosphorus atom should the melt contain? Melt. In it is given that 10 to the power 16 phosphorus atoms in the solid state. Obviously, the ingot content means that means the solid. Ingot means the raw crystal. Ingot means the raw crystal, as grown crystal. You have not sliced it into wafers. So, that crystal is known as ingot, that is basically the raw crystal. It is 10 to the power 16. So, what concentration of phosphorus atom should the melt contain to give this impurity concentration in the crystal? So, melt must be 2.8 into 10 to the power 16 centimeter cube inverse, right. So, you see that the melt contains more phosphorus than the ingot. The melt contains 2.86 into 10 to the power 16. The ingot contains 10 to the power 16, that means 1/3 almost. That means almost 1/3. So, 2/3 of the phosphorus is rejected in the melt itself, right. Now, this amount of phosphorus we have to convert it into weight, right. How you can do? See, this phosphorus per centimeter cube of the melt. Now, what is the volume of the melt? Melt volume is how much melt was there? 5 kg. So, that means 5000 gram of silicon divided by density of silicon. Density of silicon is how much? 2.33, but the molten silicon has higher density than the solid silicon, and it is 2.53 gram per centimeter cube. yes, 2.53 and normal silicon is 2.33 as per the data obtained in the literature. So, if you calculate this thing, so what you will find that it is 1976 centimeter cube of silicon. Here one thing I must clear, that only I have considered the melt consists of silicon only. Yes, what is there in the melt? Silicon plus phosphorus, but the amount of phosphorus is very less. I shall show you. That is why in solving such problem, always you take the volume of the melt as the volume of the silicon or gallium arsenide. That means the constituent host, the host crystal basically. 1976 centimeter cube of silicon, and you see that Cl is this per centimeter cube phosphorus. So, amount of phosphorus is how much? 2.86 multiplied by 10 to the power 16 into 1976 centimeter cube, it is centimeter cube inverse. So, you will find 5.65 into 10 to the power 19 phosphorus atoms. 5.65 into 10 to the power 19 phosphorus atoms. Now, you use the Avogadro number. How you can use? You see that 5.65 multiplied by 10 to the power 19 atoms into atomic weight of phosphorus is 31. It is at this gram per mole divided by 6.023 into 10 to the power 23 atoms per mole. So, that is equals to 2.9 into 10 to the power minus 3 gram of phosphorus. That means how much? It is almost 3 milligram. 2.9 into 10 to the power minus 3 gram means almost 3 milligram. So, what you find that for 5 kg of silicon to obtain 10 to the power 16 per centimeter cube carrier concentration, 10 to the power 16 concentration means 10 to the power 16 electrons. You need only 3 milligram of phosphorus atom. Problem. Okay. You come to this problem. Yes, 10 to the power 16 phosphorus atoms were there, and first thing is that what concentration of phosphorus atom should the melt contain. We have seen that it is 2.86 into 10 to the power 16, and finally, we see that only 2.9 milligram of phosphorus is to be added. So, that is the beauty of the doping in semiconductor. 5 kg of silicon is doped by only 2.9 milligram of phosphorus to get a concentration of 10 to the power 16. If you want 10 to the power 16 to be 10 to the power 17 or 18, then 2.9 will be increased, but not in the value of kilogram or gram. It may be several milligrams, right. And where this phosphorus goes? Where this phosphorus goes? They occupy either the vacancy position or the interstitial position. There can be another kind of example, say this is another example. You can practice it. a silicon ingot which should contain 10 to the power 16 boron atoms per centimeter cube is to be grown by Choralsky technique. What concentration of boron atoms should be in the melt to give the required concentration in the ingot? Same problem. If the initial load of silicon in the crucible is 60 kg, how many grams of boron with atomic weight 10.8 should be added? The density of molten silicon is given 2.53 gram per cc, and also K zero, the segregation coefficient is given, it is 0.8. Same type of problem. And here the result I can give you, you please write down the result so that you can practice and you can compare. It is 5.31 milligram. It is just 5.31 milligram. That means, for 60 kg of silicon, if you dope with boron to obtain 10 to the power 16 concentration, only 5.3 milligram of boron is required, very less amount for 60 kg. So, what we see that the doping concentration can be calculated once you know the segregation coefficient using the same expression which we have deduced. Okay.